Welcome to this explainer. Let's just dive right into a scenario I'm sure we've all experienced at some point. Imagine this. It's pouring rain outside, the wind is just howling, and suddenly, bam, the electricity goes out. Everything goes completely silent, and your house is pitched in total darkness. But a few moments later, maybe someone outside fires up a heavy diesel generator. It roars to life, and within seconds, the lights turn back on, the ceiling fan starts spinning, and your phone lights up because it's charging again. Just like that, everything is back to normal.
But have you ever stopped to actually ask yourself, where did that electricity suddenly come from? Think about it logically for a second. There are no massive, hidden batteries stuffed inside that generator holding a charge. Nobody is magically creating electric charge out of thin air. You're just burning fuel to turn a crank. So how does simply rotating a loud mechanical machine suddenly produce the invisible electrical energy that powers your entire home?
To figure that out, let's jump into Section 1, the electricity mystery.
To really appreciate this, we've got to flash back about 200 years. By 1820, scientists already knew something pretty fascinating, and we have Hans Christian Ørsted to thank for it. He discovered that whenever an electric current flows through a wire, it naturally creates a magnetic field right around it. Electricity creates magnetism. This absolutely amazed the scientific world. But it immediately raised the reverse question. If electricity can create magnetism, is there any way magnetism could create electricity? Well, nobody knew, at least not until 1831, when a brilliant scientist named Michael Faraday decided he was going to find out. So Faraday actually set up a physical experiment to test this. Imagine a simple coil of wire, and it's connected to a galvanometer, which is just an instrument that tells us if a current is flowing. Okay, step 1. He brings a magnet close to the coil and holds it completely still. What happens? Absolutely nothing. Zero current. Step 2. He pushes the magnet into the coil. Suddenly, the galvanometer needle deflects. We have electricity. But then he stops moving the magnet, and again, nothing happens. Step 3, he pulls the magnet out. The needle deflects again, but this time it moves in the exact opposite direction. And just like that, Faraday changed the world. He figured out that the magnet just sitting there wasn't doing anything. The secret sauce wasn't the magnet itself. The secret was change. As long as the magnetic field passing through that wire coil was actively changing, getting stronger as he pushed it in or weaker as he pulled it out, electricity was born. If things stayed the same, nothing happened. This right here is the heart of electromagnetic induction. A changing magnetic field produces an electric current. Now, to really wrap our heads around this, we need to know exactly what is changing. Physicists call it magnetic flux. Think of it like this. Imagine you're standing out in that heavy rainstorm from the beginning of our explainer, and you're holding a big circular hoop. If you hold that hoop perfectly flat against the falling rain, a ton of raindrops pass straight through it. If you tilt the hoop, fewer drops make it through. Magnetic field lines work basically the exact same way. Magnetic flux is simply the total amount of magnetic field that's passing through a specific area, like the open space of our wire coil. So the total amount of this magnetic flux basically boils down to 3 things. First off, the strength of the magnetic field itself. A stronger magnet is like a heavier, crazier downpour of rain. Second, the size of the area inside the loop. A bigger wire loop is going to catch way more of those magnetic field lines. And third, the angle between the field and the surface. Just like tilting that hoop in the rain. If you mess with any one of these, change the strength, shrink the size, or tilt the angle, you are actively changing the magnetic flux. But hold on, because Faraday had another real game changer of a realization. Electricity isn't produced just by having magnetic flux sitting there. It's actually produced by the speed at which that flux changes. It's all about how fast it changes. The faster you shove that magnet in, or the faster you spin that coil, the greater the induced voltage or electromotive force you're going to create. Which brings us to this absolutely beautiful, world-changing equation, Faraday's law of electromagnetic induction. E equals negative d phi over dt. Now, don't stress about the calculus notation for a second. In plain English, this simple little equation is just saying that the electrical voltage you get, that's the E, is directly tied to exactly how fast the magnetic flux, the phi, is changing over time. And it's no exaggeration to say every single generator on Earth, from your car's alternator to the Hoover Dam, runs entirely on this one rule. But wait, look at that formula again. Did you catch the minus sign sitting right there at the front? Is that just some random math formatting thing? Actually, no way. That tiny minus sign is doing some really heavy lifting. It represents one of nature's most stubborn, unyielding, and honestly kind of beautiful rules. Picture this. You're pushing that magnet into the coil. Current is induced, right? Well, that newly induced current immediately creates its very own magnetic field. And what does this new magnetic field do? It actively pushes back against you. It literally opposes your motion. If you try to pull the magnet away, the induced current flips and tries to pull it back, doing everything it can to stop that change too. This physical resistance actually has a name. It's called Lenz's law. The induced current always opposes the change that produces it. And you know what? That is exactly what that negative sign means. It's a fundamental rule that nature just naturally resists sudden change. It doesn't want the magnetic field to increase, and it doesn't want it to decrease either. It just pushes back. And this brings us to a seriously crucial realization about the universe. We aren't magically creating energy out of thin air here. Because the coil naturally resists your motion thanks to Lenz's law, you actually have to push physically harder to move that magnet. The extra mechanical work you're doing with your arm to overcome the coil's resistance, that is exactly what converts into electrical energy. Energy is simply changing form, which keeps the law of conservation of energy perfectly intact. Mechanical energy literally becomes electrical energy. Okay, so practically speaking, how do we actually pull this off in the real world? Well, we just need to keep the flux changing, right? So we can move the magnet back and forth, we can move the coil itself, we can spin the coil in circles, we can spin the magnet, we can even alter the magnetic field strength without moving anything. We've got all these different tricks up our sleeve, but they're all just different ways to do the exact same chore. Keep that magnetic flux in a constant state of change. Which brings us right back to the question from the very start of our explainer. How does a massive generator actually produce electricity? How do we take Faraday's simple little wire, coil, and magnet and supersize it to power entire cities and nations? Let's look at a huge hydroelectric dam to see how it works. Step 1. Millions of gallons of water stored way up high violently crash downward. Step 2. All that heavy flowing water smashes into the blades of a giant turbine, spinning it super fast. Step 3. That spinning turbine is hooked right into a massive generator. Step 4. Inside that generator, huge magnets are physically forced to spin around giant stationary coils of copper wire. And Step 5. Because those magnets are spinning relentlessly, the magnetic flux passing through those coils is endlessly changing. And boom, that changing flux pumps out a massive amount of electricity.
So how does all of this power our lives? Let's get into Section 5, powering the modern world.
Think about a giant hydroelectric dam. Flowing water spins a turbine. That turbine rotates massive magnets inside huge coils. What about a wind turbine? Well, moving air spins the blades, rotating the generator. A thermal power station? Burning coal heats water into steam, and that steam spins the turbine. Even a nuclear power station just uses nuclear heat to create steam to, you guessed it, spin a turbine. And honestly, this is the most powerful realization of this entire explainer. The energy source, it changes. You can use water, wind, coal, or even uranium. But the principle remains exactly the same. No matter what fuel source is powering our modern world, the final step of converting mechanical energy into electrical energy is always spinning a magnet and a coil. It is always Michael Faraday's electromagnetic induction. But, our story isn't quite over yet. We figured out how to generate tons of electricity at the power plant. But how does it travel hundreds of miles across the grid through those tiny wires without just losing all its juice along the way? How does it safely step down to the exact right voltage before it hits your wall socket?
Well, the answer to that question lies in another incredible engineering marvel, built entirely on the exact same principles of changing magnetic flux that we've uncovered today. And that is exactly what we'll be covering in our next explainer on alternating current and transformers. You really won't want to miss how the rest of this journey unfolds. So what do you think? Are you ready to see how we tame this massive power? Thanks for exploring the spark of motion with me today, and I'll see you in the next one.